Okay, so I'm going to give you a couple definitions here. Write down an abbreviated version or the full. I don't really care, but you just need to know, in essence, what it is. Okay, so chemical bonds are mutual attractions between the nuclei of, the nuclei and valence electrons of different atoms. Okay, so a chemical bond, there's a couple different types we're going to talk about, but in general, a chemical bond is an attraction between the nucleus of one atom and the valence electrons of another atom. This is how I will always represent valence electrons. Okay, do you want a reminder about what valence electrons are? Do you remember? The outermost electrons. Okay, so it's in a shell of an atom. The outermost electrons, sorry, you can't really see that, valence electrons. The outermost electrons are called the valence electrons, and those are the ones that are available for bonding. Okay, so valence electrons, sorry. Those are the ones that are available to bond. So how many valence electrons does nitrogen have? Look on the periodic table. Hold them up. Hold up your fingers. How many do they have? Luckily, it fits on one hand. 5. Valence electrons are 5 because it's in group 5 or 15, right? Count over the group numbers. Hydrogen's in group 1, they all have 1 valence electron. Beryllium, magnesium, group 2, they have 2 valence electrons. Skip the transition metals. Boron is group 3 or 13, they have 3. Carbon's 14, it has 4, 5, 6, 7, 8, right? The noble gases have 8 valence electrons, which means they don't like to bond, right? All right. So chemical bonds. There's 2 types of chemical bonds that we're going to talk about. The first of which is called an ionic bond. And what are ionic bonds? We know that ionic compounds are made up of what types of elements? What 2 types of elements? Metal and a nonmetal. Good. So ionic bonds are between a metal and nonmetal. Okay, or we can also think of it as between a cation and an anion. Okay. What happens specifically in these types of bonds is that they give up their electrons to other atoms. They don't share them, they completely trade them. So in an ionic bond, we have a trading of electrons. Okay, that's what happens in an ionic bond. They trade their electrons, or they completely give them up to one, and another one takes them away. Right? So what happens in an ionic bond, I'll show you kind of what that looks like, but let's say sodium gives up its electron to chlorine, right, to form sodium chloride. Okay, what happens is chloride now takes on a -1 charge, sodium now takes on a +1 charge, and those charges want to hang out really close to each other to kind of neutralize. That's what happens essentially in an ionic bond, right? They trade their electrons completely, but then that positive and the negative charge attract each other so closely that we consider it what's called a bond. Okay, that's the overview of what happens in an ionic bond. Does that make sense? Trade them, they form charges, then they stick together. Okay? So that's an ionic bond, right? Do we have what we need here? All right. Second type of bonding is called, anyone know? Yeah, good guess, covalent. Hopefully that was on the tip of everyone's tongue. Okay, covalent bonds. What would we assume covalent bonds are between? Nonmetals, right? That's what we named covalent compounds. So these are between 2 nonmetals. Okay, what happens in a covalent compound is that these guys share electrons. So they kind of share to make each other happy, to complete the octet, right? These guys are all about the sharing, okay? And these are the non-metals. So what side of the periodic table would that be on? The right side. Good, right? Carbon, nitrogen, oxygen, those guys are all good sharers, okay? So they share to complete what we call the octet, right? The difference, or something else we need to think about in covalent bonds, is that sometimes they share equally. And sometimes they don't. Okay, so sometimes they're like, yeah, sure, I'll take the electrons, you can have some of mine, we'll share. And other times they're like, no, I'll look like I'm sharing because my mom's looking, but I really want more. Okay, that's kind of what it's like. No one even laughed at my lame joke. Thinking back to what we know about how badly electrons want to be taken, right? Do we have an idea about what elements might share unequally? Okay, or what elements might want electrons more than others? Group 7 might want electrons really, really badly, right? Because they only want one more electron to fill their octet. What one element specifically wants electrons the most? Fluorine. Fluorine wants electrons the most, right? And I'm going to give you a little table today to show you that, okay? So something that we need to think about when we look at bonds, right? Bonds are just between two atoms. It's rare to have a bond that is 100% ionic or 100% covalent. Okay, perfect sharing or perfect trading. Most of the time they kind of fall somewhere in between the two. All right, and we're going to look at a kind of a sliding scale that goes with that. Okay, I'm going to hand out to you what's called the Pauling scale. Okay, so if you want to write on it, you can. It's a Pauling. Pauling. This is the last name of a guy who came up with it. Surprise, surprise. Okay. You can just leave him back there. That's fine. Look at the Pauling scale. Does it confirm to us that fluorine is the most electronegative? Yeah, it has the greatest value, right? It's even color-coded for you. So you see the darker we go, the greater the electronegativity. All right. I know that some of those numbers are a little bit difficult to read, but hopefully you should be fine reading those. Do you notice that the noble gases are cut off there? Okay, why do you think that is okay that the noble gases are cut off? It's a full octet. Do they want electrons at all? No, they don't bond, so they don't even have an electronegativity value assigned to them. They don't even want them at all. Okay? So now let's take a look at how we determine if these electrons are shared evenly or unevenly, or if it's an ionic bond. There's things like that. Okay? So what if electrons share, but they're more electronegative or less electronegative? Okay, so we're going to talk about covalent bonds in a little bit more detail right here. Okay. So this is talking about the sharing of electrons, if they're shared evenly or unevenly. Okay, so within a bond, that's what we're looking at here. Electrons can be shared evenly or unevenly. So what we would call a polar covalent bond, so a polar bond or a polar covalent bond, however you want to say it. This means that the electrons are shared or distributed unevenly. Okay, so polar covalent bonds have an uneven distribution of electrons. That means between these two atoms, one of them is pulling the electrons closer to them than the other. Right? Can we visualize here? Let's say I'm fluorine and Macy is carbon. Okay? Would the electrons sit right in the middle of us? What do you think? Who wants the electrons more? Me, fluorine, or Macy, carbon? Fluorine, right? I do. That means they're going to like slide this way closer to me. Okay, so it's kind of like that sliding scale. There's 2 electrons between us, right? We're each contributing 1. They're going to sit a little bit closer to me, though, because I want them more. Okay? That's how a polar covalent bond works.
What does it say right there, like right off the page?
Oh, electrons, sorry. I need to fix my projector. Okay. Electrons are shared or distributed evenly. Unevenly. Sorry. Okay, they are shared or distributed unevenly. Okay, so that is a polar bond. Opposite of that, we have something called a nonpolar bond. Okay, so what do you think might happen here? The electrons are in the middle, good, or electrons are shared or distributed evenly. Okay, so this is a little bit counterintuitive, right? Non-polar means even, and polar means not even. Okay, it's kind of, I think, a little bit funky with the way the words are associated there, but that's how it goes. Okay, so polar means uneven distribution of electrons. Non-polar means that they are evenly shared. Okay. Let's go ahead and open up your book to page 176. It gives a couple examples for us to look at. All right, so on this figure 2 on page 176, we see that there's a kind of a bluish purple region that is considered an ionic bond. Okay, that means there's no sharing going on, right? That just means that we kind of trade and they become kind of a little bit separate entities, right? That's an ionic bond. So they are shared so unevenly that it's not even considered a covalent bond anymore. Does that make sense? Okay, so they're pulled one way or the other to such an extreme that we don't consider it a covalent bond anymore. When we get down into this kind of green region, we consider it a polar covalent bond. Okay, and that means that they're shared unevenly, but they're still shared. Okay, and then the very bottom there with the all green is the non-polar covalent. So that means those electrons are shared almost exclusively in the middle, right? They are very, very even. Okay, do we see these numbers on the left side of that table, right? 3.3 to 1.7 gives us an ionic bond. 1.7 to 0.3 gives us a polar bond, and 0.3 to 0 gives us a non-polar covalent bond. Do we see those values? We can determine those values based on the Pauling scale. Okay, so if I wanted to look at a bond between, let's say, oxygen and bromine. Okay, I wanted to look at a bond between oxygen and bromine. We know these are 2 types of what type of elements are these? Metals, nonmetals? Nonmetals. So we can guess it's going to be in the covalent range, right? It's going to be because these are 2 nonmetals. Okay, let's look at the electronegativity value for each of those 2 elements, right? We're just looking at a single bond between those 2 elements. Let's look at the values for those. Okay, oxygen has an electronegativity value of what? 3.44. Bromine has an electronegativity value of what? 2.96. Okay, so we want to subtract those. You're always just going to take the bigger from the smaller. There's no negative when we look at bond values. Okay, so 3.44 minus 2.96. I guess there is a little math. Okay, did I do that right? Hopefully. What range does this fall in? Polar covalent. Okay, so this would be a covalent bond. And which way would the electrons shade toward? Which way would the electrons be pulled? More towards oxygen or more towards bromine? Oxygen, because oxygen has the larger electronegativity number. So the electrons would be a little bit more on oxygen side between this bond. Okay? Why don't you go ahead and write down that table in your notes somewhere, or even just the ranges. 1.7 to 3.3 gives us an ionic bond, 0.3 to 1.7. That can go either on your Pauling scale if you want, or it can go in your notes. That's fine, either way. Okay, but just get... the percentages are the percentage of ionic character. We don't have to know that. It's kind of like what percent of an ionic bond is it. All right, we're going to look at some examples between sulfur and lithium, sulfur and hydrogen, and sulfur and fluorine. Okay, we're going to look at each of these. Okay, these bonds right here might be part of a larger compound, but remember, within a compound there might be 10 bonds, right? So there's polar bonds or nonpolar bonds or whatever bonds within a certain compound. There could be lots of different bonds. We're looking at individual bonds between two elements. Okay, so between sulfur and lithium, sulfur's electronegativity value is sulfur. Oh, that is 2.58. Okay, that's why I had. So if you want to write that in a little bit better on your Pauling scale, you can. But sulfur is 2.58. Okay, lithium is 0.98. Should we be able to see what type of a bond this is just right off the bat without even doing any calculations?
Yeah.
Why do you think that?
Where it's located on the...
Exactly, where it's located, right? Sulfur's a non-metal, lithium's a metal. We should know right off the bat that it is an ionic bond. And if we do the subtraction, we get 1.60. It falls within the polar covalent. What do we really know about sulfur and lithium though? It's an ionic bond. Okay, so this is an ionic, but it's shared just enough that we would consider polar covalent. Okay, those iffy ones like that, I'll really take either one. Okay, we know that it's between a metal and a non-metal, which we usually classify as an ionic bond. Okay, but this is showing us that lithium is willing to kind of give it up just a little bit, or it wants to kind of pull them back a little bit. So I kind of look at either one here. Okay. Technically, according to our scale, this would be a polar covalent, however. Okay? That was not a good one for me to start on. Okay, let's look between sulfur and hydrogen now. Okay. Sulfur is 2.58. Hydrogen is 2.20. Okay, so a 0.38 difference gives us what type of a bond? A polar covalent bond. Good. So they're shared. Which way are they going to lean toward? The electrons are going to lean towards sulfur here. Okay, just like in the first one too, they're going to lean towards sulfur.
So on like a test or quiz, or how are the questions going to be formed? Are you just going to give us two?
Yeah, I might just give you two. And I won't give you ones that are iffy like that one, I make them a little bit clearer. Not a good example for me to start with. Okay. Last one, sulfur and fluorine. Okay, sulfur is 2.58. Fluorine has a value of 3.98. Okay.
Do we always put the bigger one on top?
Yeah, you always would just subtract bigger from smaller. You will never have a negative. Yeah. Good question. Okay, so a value of 1.40 with our electronegativity difference would tell us it's probably what kind of a bond? Polar covalent. Good. Okay. I want to look at one other example here. What if we had a bond between sulfur and sulfur? Yeah, non-polar covalent. We don't even have to do the math, right? If it's between the same element, we have to know that that's going to share equally. Each of them wants the electrons the same amount as the other element. So if it's between two of the same element, we know it's automatically a non-polar bond. Okay? So covalent bonding, they share electrons. The reason that these covalent bonds happen is that we share electrons to, let me make sure you can see that, to be able to complete the octet. Okay, and how many electrons are in the octet? 8 electrons. Okay, so what happens in a covalent bond when they share? They can kind of take into account each other's electrons. Okay, we're going to share these so that they can start to kind of complete each other. Okay, that's what's happening with a covalent bond. Right? They want to form the octet, which is 8 outer electrons. Not 8 total electrons, 8 outer electrons. Okay? All right. Before we get into the octet rule, I want to talk about a few kind of exceptions, right? The octet rule just means that we want 8 outer electrons. I'm not going to put outer, 8 valence electrons. Okay, that's the octet rule. Every element wants to complete the octet. That's every element's goal. Okay, so every single atom wants to complete the octet. But of course, there's exceptions to the rule. Of course. Okay, because things can't be simple like that. All right, so there's some exceptions to the rule, and some can have more than 8, and some can have less than 8. Okay, so there's a few that have exceptions to that. So I'm just going to write down a couple of the big ones. Exceptions to the octet rule are boron, phosphorus, sulfur, maybe astatine. Ones that are in group 3, like boron, aluminum, those like that, they have 3 valence electrons. So that means they might only get 3 things to bond with them, which wouldn't give them a full octet. So that's okay, right? So boron might only use 3 bonds, okay? Phosphorus and these guys, they might have what we call an expanded octet, which means they can hold more than 8 electrons in their outer shell. They might be able to hold 10 or 12 or whatever. So these guys can have more than 4 things bonded to them. Okay. We'll see examples as we go along, and you really just have to kind of trust the chemical formula that goes with it. As we start to draw and we start to draw our structures, you'll be able to kind of see what I'm talking about here with these expanded octets, or incomplete octets they're called, but I want to give you those couple exceptions first. Okay, now we're going to get into our representation of atoms and representation of compounds with what we call Lewis structures. Any questions on the octet rule? Okay, octet rule means how many electrons do we want? 8. 8 total valence electrons. Okay, and then we've got some of these guys that are exceptions. Okay, so we're going to start now something we called Lewis structures. Sometimes your book calls these electron dot notation. Okay, I don't call it that. But all these are basically pictures or visual structures, 2D structures that show us what compounds look like. Okay. So we can draw a Lewis structure of both an individual atom and of a chemical compound. Lewis structures can go from extremely simple to extremely complex, depending on how big your molecule is. So we're going to start with the very, very basic. Okay, we're going to draw a Lewis structure or an electron dot notations for individual atoms first. Okay, so let's start with oxygen. No, I don't want to start with oxygen. I want to start with fluorine. Sorry. Okay, let's start with fluorine and its electron dot notation. How many valence electrons does fluorine have? 7. Okay, so this is all it is. 1, 2, 3, 4, 5, 6, 7. That's fluorine right there. That's it. Electrons are indicated by dots.
Does it matter where you start?
Doesn't matter where you start. Mm-mm. And most of the time we want our electrons in pairs, okay? But fluorine has an odd number, so we don't have a pair there, okay? Most of the time we want them in pairs, okay? Let's look at now if fluorine bonded to another fluorine. Okay, we're going to start with the simple one. So fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Okay. Let's say these two wanted to bond with each other. What type of a bond would it form? A nonpolar covalent. Good. Okay. So let's say these two want to bond, and in a nonpolar covalent bond, do they share or do they trade? They share. Okay, so let's say that fluorine comes over here and shares that electron. Okay? Now, let's look at what happens with our octet rule. We've now formed a chemical bond, right? We've taken an individual fluorine and individual fluorine. They've come together to share that valence electron, that outermost electron, to form a chemical bond, right? This is a nonpolar covalent bond. Okay, and now let's see if we've completed the octet, right? We know each element wants to complete the octet. We're going to count our electrons for each individual atom. Okay, let's look at fluorine here. This red fluorine, okay? 2, 4, 6. And then how many electrons are found in this bond between them? 2. So that's 2, 4, 6, 8. It gets to count both of those electrons when we're searching for the octet rule. Okay, so once we've bonded something, we get to count the electrons within that bond as part of each atoms. Okay, so this red fluorine is good. Now let's look at the blue fluorine. It has 2, 4, 6, 8, right? Did they each complete the octet rule? That is a good bond, okay? So what happens here is we took each of these fluorines, we smashed them together, they shared electrons. If we were to draw the actual Lewis structure with that, when we have a bond, we now represent it as a line, okay? So we would say fluorine, fluorine, and then we would fill in those extra electrons along the outside. Okay, so this is a Lewis structure of the F2 molecule. Okay, we went from a dot structure of one single atom, combined it with another to build that Lewis structure. Okay, so if I asked for a Lewis structure of F2, this is what you would tell me. Okay, and I'll show you a much simpler way to get there. We just want to start from the very beginning and work our way in. Okay, so let's check our work here. Lewis structures have a way to check yourself. Okay, so within this F2 molecule, how many valence electrons are there total? No. Each fluorine molecule gives 7, which gives us 14 electrons. So even though we've completed the octet rule for both elements, which would make us think 8 and 8 is 16, that's not how it works, right? We should have 14 electrons represented somewhere in our Lewis structure, okay? Here's 2, 4, 6, 8, 10, 12, 14. Okay, so when we count that bond, we get to count it for the octet for each one. But when we count total electrons within the compound, there are 2 electrons within this bond, 1 from each fluorine. Okay, is that kind of making sense? Kind of not? We're going to do a lot more examples. We're going to get a lot more into it, but this is just a very simple start. Okay? Let's try another compound here. Okay? Let's look at the Lewis structure for CCl4. Okay? We're getting a little bit more complex here. I'm going to show you one example, then I will go through and give you all the rules for drawing Lewis structures, and then we'll do some more examples. Okay, so just go with me for this first one, then I'll give you the rules, and we'll go back and do some more practice. Okay, so I'm going to talk through it one time, then I'll give you all the rules for sure. Okay, so here's our compound. We want to represent this Lewis structure. First of all, do we think that each of these bonds are going to be ionic or covalent? What do we think? Right, there's going to be a bond between carbon and chlorine, another bond between carbon and chlorine, carbon, chlorine, carbon, chlorine. Okay, 4 bonds total. They're going to be covalent, right? Because carbon and chlorine are both non-metals. Okay, so they're going to be covalent compounds. Covalent bonds. Could be polar, could be non-polar. We haven't looked at that yet. And we don't really care at this point. Okay? So here's how I'm going to draw my Lewis structure. I'm going to start with the least electronegative atom. That always gets to be in the center of our Lewis structures. Okay, least electronegative gets to be the middle. From there, I need to bond 4 chlorines to that carbon. Okay, so I'm just going to go in each direction. Chlorine, 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 chlorine. Okay. Again, I will give you the rules and I'll give you the process to how to go through this, but we're going to look at it first, okay? We're going to bond each of these chlorines to the central atom, to carbon, right? Because that's what our structure is. Carbon bonded to 4 chlorines. Okay? So now let's check how many electrons do we have represented so far. How many electrons are in this bond? Okay, there's 2 in this bond, 2 in this bond, 2 here, right? So far we've got 8 electrons. Okay, do we think that's enough total electrons for our... No. Probably not, right? Okay, so now let's check. Carbon has how many valence electrons to give? 4. Look on the periodic table, right? Chlorine each gives us 7, and there's 4 of those. Okay, so that's 28 plus 4. Total, we should have 32 electrons represented on our Lewis structure. Do we have 32? No, we only have 8. Okay, so that's no good. So now we need to start looking at completing the octets. Is carbon's octet complete? Yeah, 2, 4, 6, 8, right? It gets to count all of those shared electrons in its octet. Is this chlorine's octet complete? No. So we need to start adding electrons. Here's the rule for when we add electrons. We always add them in pairs. Okay, we call these things lone pairs because they're not bonded to anything. So here's 2, 4, 6. That would complete chlorine's octet. Right? 2, 4, 6, 8. 2, 4, 6, 8. Okay, my mouse is a little slow today. So we've used 6 more electrons. Okay, we used 8 to begin with, then we used 6 more. Okay? Oops, I don't want to do that. Now let's do this for each chlorine because we want to complete the octet for each chlorine. Okay, so we're going to add 6 electrons to the outer rims of each chlorine. Okay, so now we check our octets. This chlorine has 2, 4, 6, 8. This chlorine has 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Okay, so the octets are all good. Now we count our total electrons. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Is that what we needed? Good to go. Okay, so I know that's kind of a long process, a little bit new. We're going to go, I'm going to give you the set of rules now, and then you'll be able to apply those rules for each compound. Mm-hmm. And these rules are going to go a little bit out of order from what I did in my demonstration, but it's going to make more sense for you when you start out drawing these. Okay, first rule. Again, a little bit out of order from what we went, but this will be simpler for you. Okay, so the first rule is to find the total number of valence electrons. Boys. Okay, find the total number of valence electrons. So when we added up carbon and the 4 chlorines, right, to get 32 electrons, we did that later on. That should really be your first step. Okay, so whenever we're given a compound, the first thing you do is find the total number of valence electrons. Okay, so the outermost. Okay, so that's rule number 1. Number 2, you're going to arrange the atoms in the what we call the skeleton. Okay, and all the skeleton means is that it's the elements themselves without bonds and without lone pairs. Okay, so it's just the elements kind of put in the right spot. No bonds yet, no lone pairs. You're just putting in what you think might be the right position. Okay, so that's the skeleton. So there's some parts to the skeleton that we have to think about. Okay, what element goes in the middle, right? What can't go in the middle? There's some rules that go with that. Okay, so if you have carbon, so carbon will always go in the center. Okay, so carbon is always a central atom, or it has the ability to be. Anytime you have carbon, it's going to be in the center. Okay, things are going to be bonded to it. It's not usually an outer element. Okay, so carbon's going to be always in the center of the skeleton. Okay, so what happens if you don't have carbon in your molecule? Okay, so if you have carbon, it always goes in the center. If you don't have carbon, I'm going to move on here. Do we have what we need here? Okay. If you don't have carbon, so if no carbon, then the least electronegative atom is the central atom. Okay, so if you have carbon, it always goes in the center. If you don't, then you look to the least electronegative atom to go in the center. Right, so least electronegative would be farthest from fluorine, or the lowest electronegativity value on this Pauling scale. Okay, least electronegative goes in the center. Last rule for the skeleton is that hydrogen can never be a central atom. Hydrogen can never be a central atom. How many valence electrons does hydrogen have? 1. That means it can only bond to one thing. So how can it be a central atom if it can only bond to one thing? Not going to work. Does hydrogen ever complete an octet? That's the exception to the octet rule as well. Hydrogen doesn't complete an octet. It only has 1 valence electron to give. It's not going to complete it. It's just giving that 1 electron. It's going to be bonded to one thing. That's it. Okay, so hydrogen only has 1 bond. Never a central atom. Okay, so there's our little subparts to the skeleton. Rule 3. Once you have the skeleton drawn, you will bond the central atom to each outer atom. Oh my. Okay, outer atom. Okay, and then you'll fill in your electrons. So fill in lone pairs. Okay. Last thing I want you to write big on your notes and your rules. Hydrogen can only bond to one thing. Okay, it cannot have 2 bonds, or 4 bonds, or 10 bonds, however many things you want to do to it. Not going to happen. Okay, one thing. That's it. All right, our first practice problem is going to be NH3. No charges yet. We're not going to deal with charges yet. Okay? We're just dealing with... Can anyone name this molecule? Doesn't have a charge. No charge. That makes a difference. Yeah, there we go. Nitrogen trihydride. Perfect. Nice job. Okay. If it was a NH3 plus 1, then it's ammonia. Okay. First step. What is our first step? Find the valence electrons. So nitrogen has, from the periodic table, we know it has 5. You can get your periodic table, your regular periodic table out if you want, or you can just look on here, right? Group 1, 2. It even has the group numbers on here. So, okay, hydrogen has how many valence electrons? 1, and there's 3 of them. So that gives me a total of 8. Okay, so we need 8 electrons represented somewhere in our structure. Okay, second rule, build your skeleton, right? Which could be our central atom here?
Hydrogen.
Good. Nobody better say hydrogen. Okay, nitrogen is our central atom. Then we arrange our skeleton, right? So we're just going to kind of space these hydrogens out. We'll get more into where they should properly be spaced later, but right now we're just working on a simple 2D structure. Okay, so we've got our skeleton. 3 hydrogens, 1 nitrogen, all accounted for. Okay, so now next step is to bond. How many electrons have we used up so far right there? No, we've used up 6, right? 2 in each bond. 2, 4, 6. So if you want to do it this way, you can take your total number. We've used 6. That means I have 2 left. Okay, where would those 2 probably go? On nitrogen, that's right. Okay, so now we check, did we complete our octets, right? Hydrogen doesn't get to complete an octet, so we look at nitrogen. Nitrogen has 2, 4, 6, 8 electrons. There's its octet, and it's also the total number that we needed to use. So there is our Lewis structure for NH3. Right, not so bad, huh? Okay, always go back and check to make sure we've got octets completed and we've got the total number of valence electrons correct. Okay. Any questions here? Yeah, Colin.
Is that another line under nitrogen?
No, that's just a check mark. Sorry. All right. Ready to try another one? Yes. Okay, H2S. H2S. Okay. Hydrogen each has 1, and there's 2 of those. Sulfur gives us 6. Okay, so we should have 8 valence electrons here as well. Okay, we build our skeleton. If we've got 2 things that are bonded to the central atom, we just want them to be opposite of each other, right? They should be spread out, as far as they can. So don't put it like this, right? We don't want it to make an L shape. We're going to spread those out as much as we can. Okay, so here's our skeleton. Next step is to bond to each of those outer atoms. How many have we used so far? 4. So we've got 4 left to use somewhere. where do they probably need to go? Sulfur. Okay? So try the outer atoms first. If they can't take any more, then you go back to the central atom. Okay? So we used 4 more. We got 0 left. We look at sulfur's octet. Is it complete? 2, 4, 6, 8. Hydrogen's good to go because they're each bonded to one thing. Perfect. All right, feeling good? All right. Let's try this next one on your own. Okay, is that what we had? Good. All the ones we've done so far have been pretty simple, right? All 8 electrons. We're going to make them a little bit more complex. Okay, are we ready to try a couple other ones now? I don't necessarily have 8. Any questions so far on the simple ones? All right, let's look at now at ones that might have a double bond. Not just a single bond, but a double bond. Okay? So let's look at CH2O. Okay, count our valence electrons. So 4 plus 2 plus 6. Four plus 2 plus 6 gives us 12 valence electrons total. Okay, so here's kind of a clue as to what this skeleton should look like. These are called hydrocarbons that have carbon and hydrogen in them. Okay, real original. So these kind of give us a clue as to how these things are bonded together. The order in which the elements go give us a clue as to how they're bonded. So this set says CH2. That tells us that these H's are going to be bonded to carbon. And then carbon's also going to be bonded to oxygen. That's kind of what it's telling us. Okay, and that's a little bit hard to pick up on sometimes. But our skeleton should look something like this. C, O, and then we'll have H's kind of over here bonded off of carbon. Okay, so that CH2O tells us that those hydrogens are going to be bonded to the carbon. All right, so let's do our bonds to begin with here. We've used how many electrons? 6. So we have 6 left. Okay, where should those 6 probably go? Okay, so a lone pair on carbon, and then what else? Here? That uses all 6? 2, 4, 6. Okay, so now we've used all the electrons we need to. Okay, so let's say if we put our other set of electrons here. Now we've got 2, 4, 6, 8, 10, 12. We've used all of our electrons. Now let's check our octet. Is oxygen's octet good? Is carbon's octet good? No. So that doesn't work. Here's what we do when we have a problem, right? We need 2 more electrons here to be able to fill our octets. But we don't have them, right? They're not available. This is what we do. We take one of these lone pairs and we slide it into another bond. Okay? So these lone pair would then turn into a double bond. Okay? So how many electrons are contained in any bond? 2. So that means in this bond up top there are 2 electrons, and in this bond there are 2 electrons. Okay, so let's count our total electrons again. 2, 4, 6, 8, 10, 12. That's good, right? That's what we needed. Now let's check oxygen's octet. 2, 4, 6, 8. Good to go. Carbon is 2, 4, 6, 8. Good to go. So this is the correct Lewis structure for that compound. Okay? So let me give you just a couple little hints here. When possible, right, if at all possible, oxygen likes to have 2 bonds, 2 lone pairs. Okay? If at all possible, oxygen wants to have 2 bonds and 2 lone pairs. That's what oxygen wants. Okay? Group 7s, like fluorine, chlorine, bromine, they like to have 1 bond and 3 lone pairs. That's what they like to do, right? Because it uses all those valence electrons correctly. Okay, any other questions here? So we've seen the double bond. We've seen regulars. Now I'm going to show you one other little type of thing that might throw a little glitch in our... This is our last one. C2H2. C2H2. So we've got carbon, right? So we know carbon has to go in the center, but we don't just have one carbon. Two. Not quite. Bond the two together, that's right. So we're going to have 2 central atoms here. Okay, carbon are both going to be our central atoms. So our skeleton, sorry, we'll do our valence electrons first. 8 plus 2 gives us 10 electrons. Okay, sorry, carbon each has 4. There's 2 of those, which gives us 8. Hydrogen is 1 times 2, okay? 10 electrons. So we've got 2 central atoms here. So we've got carbon and carbon. The hydrogens then just need to go 1 on either side. Okay, so we bond, bond, bond. We've only used 6. So here, here. Does each carbon have its octet completed? No complete octet. That's no good. No quadruple bonds. Okay, let's say if we put in a double bond, that gives us 2, 4, 6, 8 electrons, something like this. Would that work?
Nope. Triple bond.
Nope. Triple bond. That's as much as you can go. No quadruple bonds. Only triples. Because if we do 2 here, that completes this carbon's octet, but this carbon does not have a complete octet. 2, 4, 6. That's it. We gotta have all. Okay, if we did this, 2, 4, 6. Sorry, you'd have 2, 4, 6 carbons for this electrons for this carbon, and 2, 4, 6 electrons for this carbon. So now neither of them complete their octet. Okay, so then we would slide each of these into a bond. Yeah? Hydrogen doesn't need 8 because it only has 1 electron available to bond at all. Okay, so it doesn't have enough room in its shells because its electron is so close to the nucleus to even accept any other electrons. Yeah, yeah. Good question. The other ones, when you go down, like lithium, sodium, they have room in their outer shells to take more electrons, but hydrogen doesn't. Yeah, good question. Okay, she asked why hydrogen can only have 1. It doesn't have room for any more electrons. Okay, so the correct Lewis structure for this one should be triple bond and hydrogen on either side. Okay, so now we've got 2, 4, 6, 8, 10. All of our octets are complete. All right.